Hello and welcome to the course Design Borefields with Confidence. This is the third chapter of the fifth part, and we will be talking about the importance of working with the exact borehole coordinates when designing a borefield. Because typically when you're designing a borefield, especially in the early phase, you start with a rectangular configuration, and based on that you determine the number of boreholes required to fulfill your total building demand. Now, often in practice or later on, these borefields are no longer strictly rectangular, and the boreholes are scattered around the building, or in case they are under the building, they are also scattered because you have foundation, there are other underground structures, and so forth. And this means that although borefields are typically designed in a beautiful grid, in reality they are not. And this video is all about the importance of working with this irregular grid, because it can give you some significant differences in results. So this video will not be so theoretical, it will be more hands-on. I will show you an example in GHG2 where we start with a rectangular grid and then the actual borehole coordinates as were drawn on AutoCAD. We will discuss how we can import the coordinates from the AutoCAD file into GHG2. But I also show you a quick way on how you can design irregular grids yourself in GHG without needing to go through AutoCAD and so forth. So it will be a really hands-on video talking about the long-term effects of geothermal borefields. So let's jump into that. So here we are in GHG and I already created a new project for you. Now, if you want to follow along, again, I'll go over on our textbook, because there you can download the report of the project I'm going to create here, so you can recreate it yourself. And also for your information, the AutoCAD file and so forth will also be there, so you can also try the data extraction in AutoCAD for yourself. So here we have a new project, 017 degrees. The borefield we will start with is a rectangular borefield at 15 boreholes spaced 5 meters apart. This will be our initial assumption, our initial condition. We will work with 25 volume percent of monopropylene glycol, a double U-tube heat exchanger, although as discussed in the previous chapters, feel free to play around with that. And we will work with a variable flow rate. And then for our thermal demand, you will see that we have way more heating than cooling, so we have a very significant imbalance in this case. And if we go to our results, this is also clearly visible. Here we see that we have this downward going trend. We see that we touch both temperature limits and that we are just ever so slightly below our 0 degrees threshold. But from a pragmatic reason, we say, okay, this borefield is well designed. And you see that we are also laminar in the Reynolds number, so our effective borehole thermal resistance is not that fantastic. Feel free to play around with it and try to make it better. So this is the initial condition. Now, of course, the borefield we have drawn here, it will be something different in practice. And the exact coordinates are drawn here on this example.dwg file. You can see here that all the coordinates are drawn as red crosses and they are a little bit all over the place. Now they are still 5 meters apart, but they are scattered around a little bit. And now the question is, can we export these coordinates we drawn here and import them into GHG2? And the way to do that is to select all of them. So we select all the 15 coordinates and then we type data extraction. And then we're asked to create a new extraction. So let's do that. Okay. New extraction. Go ahead and save that. Let's press next. And then we need to say which objects we need to extract data from. Now in our cases, these are the X crosses, and the crosses are our boreholes. So no, I don't need the other information. And then we see here a very long list of all the different aspects that AutoCAD saved for these X crosses. But basically the only things we care about are the positions in X and Y. So we don't need all the other information. we just need here the geometry. And for the geometry, we don't need the scale. We basically just need the X and Y positions. So let's go ahead and press next. You see here all the X, Y coordinates, and these are in meters in this case. You also don't need the count column and the name column also not, because that's just X cross in this case. So here we have just the X and the Y positions of all our boreholes as they will be installed in practice. Let's go ahead and press next and say, well, let's output this data to an external file. And this will create for us a CSV file that we can then import into GHE2. So let's go ahead and call this example coordinates. Save it as a CSV file. And then we can press next and finish. And now we have, as said here, created a CSV file with all these coordinates. And if we now jump back into GHE2 and let's duplicate the scenario, now we can say real coordinates, and we can jump over to the customized borefield tab. And here you see that we can enter the X and Y coordinates. Now in GHE2, you can enter the boreholes by coordinates. You can even specify the depth of each borehole, which can be different. And you can also work with inclined boreholes. So basically every borefield you can think of, you can actually design in GHE2. But for now, we will just say, okay, it's X and Y, all boreholes will have the same depth, the same buried depth. It's just the coordinates that are not beautifully on a grid. So let's go ahead and load this file. So here I have my example coordinates. Let's go ahead and import that. And here I can say add coordinates to borefield or override them. Now, if you have multiple borefields scattered around and you export them in multiple files, you can just say add them to borefield, and you will hence add different systems together. In this case, let's override this 0, 0 borefield. And here you see our 15 boreholes, which are scattered around with a total borehole length that's the same as before. So let's go ahead and calculate the scenario and see how our temperature is actually different. And here you see that we have, and you see that here our minimum temperature is now almost 1 degree. So there is 1 degree Celsius difference between our rectangular assumption and our real situation in this case. Now, why is that? And in order to understand that, what we're going to do is we will make this visual by saying make a contour plot as well. And this will create a 2-dimensional temperature profile around and inside of the borefield. I will do that here as well with the rectangular case. And so we can see how the temperature behaves inside of the borefield itself. So if we scroll down for rectangular case, you see here that the temperature inside our borefield, it goes to -6, almost -6.5, -7 degrees. So you see that the cold is really trapped inside. And if we play the video, you see that the core really gets cold. And this, of course, over the years increases the downward sloping trend. And that's because of the G function. All the boreholes are close together, so their interaction is higher. Now, if we go to our real coordinates and we play here the same movie, let's start with year 1. You will see that because the boreholes are all scattered around, the cold is not really trapped inside. You have these boreholes at the outside that actually average things out. So that's why in this irregular configuration, we actually have less influence of the boreholes on each other, which gives us a better result in the end. And as a matter of fact, if I'm not mistaken, we have here 1 degree difference. So let's go ahead and make real coordinates. Let's make it real coordinates too. because we now have quite a bit of oversizing, chances are real that we can say, okay, let's go to this borehole and let's delete it. So that we can actually have the same thermal behavior with one borehole less. And here indeed we are still above the 0 degrees Celsius minimum threshold. The maximum threshold is a little bit higher, but not so much to worry about. So actually by designing with the real coordinates, you see that we can save one borehole out of 15, which is already significant, let's say. So that stresses the importance of working with the real coordinates. Now, perhaps you say, okay, I don't have AutoCAD, or it takes quite a lot of time to draw the coordinates in AutoCAD and then export them. And all these reasons are, of course, valid. Now, what you can then do in GHE is, let's go ahead to our rectangular situation again. And let's say duplicate this scenario and let's call this custom configuration. Now, if you go to Borefield, you work typically with these standard configurations. But if you click on one borehole, you can actually convert them to coordinates. And here you have the option to delete certain boreholes you don't need, so it's really easy to play around with it. But what you can also do is say, well, let's put these coordinates on a map. And by doing so, you have here a map. You can search for your address. Going to say, to make it easy, that my project is located here. And what you need to do is you need to set one reference point, basically the 0, 0 of your system. Where is it on this map? Because then all your coordinates will be drawn with respect to this specific point. So let's go ahead and set a map. And then you see all our borefields here are now drawn onto this field. Now, I want to shift all these boreholes down. So what I'm going to do is I click right and say move reference point. And then you see that all the boreholes are actually moved as well. And what you now can do is you can easily drag these coordinates around in the shape that you want. So if you have here a building, you can move them around your building or to the positions that you want. And if you scroll up, you see that your coordinates actually also change. So instead of creating it in AutoCAD, what you can do is you can go here on a map, draw them around yourself, and then you can also export these coordinates back. So you can create the irregular configuration in GHE and then download it as a CSV file. And if we now want to add another borehole, what you can simply do is you can double click and it will create another borehole. So if we now say, let's create 15 in this also scattered configuration, we go ahead and simulate this. Then we will see our contour plot below here. So we here also have a slightly higher temperature than in our rectangular case due to the scattering again of the boreholes. And here you see also the contour plot on a real map. So that's also a benefit of working with these coordinates in GHE that you can plot them on a map and actually see geographically what the influence of your temperature is inside the borefield, but also to the surroundings. And the interference between different projects, we will come back to that later in this course, but this is already, let's say, a sneak peek of what it will look like. So this was everything I wanted to say about the importance of working with coordinates and how you can do that in GHE. I hope you found this helpful and you are convinced that working with real coordinates can actually save you even money when you're designing systems. Now, in the next chapter, we will be going a little bit deeper into that. And namely, you see here that we have quite a significant imbalance, and that has a significant effect on how we should design our borefield. So the question we will ask and answer in the next chapter is how to cope with imbalance.